In this episode, we focus on a very specific kind of operational power, the ability to take a stream of text and rewrite it in a controlled, repeatable way so the next step in automation receives something cleaner and more predictable. That is the concept behind SED, which is commonly used to perform substitutions, deletions, and targeted edits on lines as they flow through a pipeline. For beginners, the danger is thinking of stream editing as a quick hack, because hacks tend to grow into dependencies, and dependencies built on fragile text assumptions are where automation surprises come from. The safer mindset is to treat stream rewriting as normalization, meaning you are deliberately shaping messy input into a consistent form that reduces ambiguity and prevents silent failures downstream. In cloud and security operations, normalization can be the difference between a script that correctly recognizes a status value and one that misses it due to extra white space or inconsistent formatting. The goal here is not to teach command sequences, but to teach what safe, repeatable stream rewriting looks like, why it matters, and how to avoid the common mistakes that cause SED-style edits to become destructive or misleading. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Normalization begins with understanding why text streams are often inconsistent in the first place. Output may come from different components with different formatting rules, or it may include variable spacing, varying prefixes, or embedded markers that are useful for humans but noisy for automation. Logs might include brackets, extra labels, or multi-part identifiers that change shape depending on context. Configuration fragments might include comments, extra indentation, or trailing spaces that are invisible to the eye but meaningful to parsers. In a pipeline, these small inconsistencies create large risks because downstream parsing often depends on exact patterns, especially when values are extracted with regular expressions or split into fields. If the upstream text varies, the same extraction logic can produce different results, which creates drift where automation behaves differently across environments. Safe normalization reduces this variability by applying consistent, predictable edits that make the text match a stable contract. When you approach stream rewriting with that purpose, you stop seeing it as a trick and start seeing it as a reliability control. A safe stream rewrite starts with a precise definition of what you want to change and what you want to preserve. This sounds obvious, but beginners often do broad substitutions because they are easy, and broad substitutions are how you accidentally change meaning. For example, removing all punctuation might simplify parsing, but it can also destroy identifiers, collapse boundaries, or merge fields that should remain distinct. Safe rewriting focuses on the smallest change that achieves the normalization goal, such as trimming trailing white space, standardizing repeated separators, or converting a known prefix into a consistent label. The key is that the edit should be intentional, testable, and reversible in the sense that you can reason about what it will do to any given line. In operational automation, you want edits that are boring, because boring edits are predictable and predictable edits are safe. When the exam asks about choosing a method for normalization, the safer option is usually the one that changes only what must be changed and leaves everything else untouched. Whitespace normalization is one of the most common and most useful stream edits because whitespace is a frequent source of hidden failures. Extra spaces can cause equality checks to fail, can shift field boundaries, and can break pattern matching in ways that are hard to see when you are looking quickly at output. Trimming leading and trailing whitespace and collapsing repeated spaces into a single separator can make downstream parsing far more reliable. In cloud operations, whitespace issues often appear when outputs are combined from multiple sources or when lines are wrapped differently, depending on terminal width or logging configuration. A beginner might think whitespace does not matter because humans can still read the line, but automation cares deeply because automation depends on exact boundaries. Safe whitespace normalization is also a form of hygiene because it reduces noise and makes the remaining content more consistent for validation. The risk is over-normalizing by removing whitespace that is meaningful, such as spaces inside values that legitimately contain them. So the safe approach is to normalize only the white space that is truly structural. This is where understanding the data you are handling matters as much as the editing technique. Targeted substitution is another common set-style pattern, and it is useful when you need to standardize variable labels or convert one representation into another. For example, one system might label a field as status and another might label it as state, and you might want to normalize both to a single term so downstream logic can treat them consistently. Another example is normalizing time formats or replacing known markers with a stable token that is easier to match. The danger with substitution is that it can match unintended text, especially if the pattern is too broad or if it is not anchored to the right context. If you replace every occurrence of a short word, you might change parts of other words, creating corrupted values that look plausible but are wrong. Safe substitution uses patterns that are specific to the context, such as replacing only when the token appears as a distinct field label or in a predictable position. This is closely connected to regular expression discipline, because set-style rewriting often relies on pattern matching to decide what to change. When you choose patterns that reflect intent and avoid accidental matches, your substitutions become reliable normalization rather than accidental mutation. Deletion and selection are also part of stream rewriting, because sometimes the safest normalization is to remove lines or fragments that are not useful and that add confusion. For example, headers, separators, or repeated boilerplate lines can clutter a stream and cause downstream logic to process non-data as if it were data. Removing those lines reduces the chance of acting on garbage and improves clarity for both humans and automation. The risk is deleting too aggressively and removing lines that contain important evidence, such as warnings that indicate partial failure. A safe operator approach is to delete only what you can confidently classify as non-essential for the current pipeline stage, while ensuring raw logs remain available elsewhere for audit and deep troubleshooting. This aligns with the broader principle of maintaining visibility while reducing noise for routine operations. When you see an exam scenario where output includes mixed content, the best answer often includes filtering or deletion of known non-data lines before parsing. The key is that deletion is not about hiding problems. It is about preventing non-data from becoming input to decisions. Safe deletion makes pipelines cleaner without making them blind. Repeatability is the central reason set-style rewriting belongs in operations automation, because you want the same edit applied the same way every time. Manual edits do not scale and do not produce consistent results, especially when multiple people are involved or when runs occur under time pressure. Repeatable edits reduce risk by eliminating human variability, and they also improve troubleshooting because you can reproduce the exact transformation that occurred in a given run. In cloud environments, repeatability is especially important because small differences between runs can cause significant differences in outcomes, and those differences are hard to diagnose if the pipeline includes ad hoc manual steps. Repeatability also supports team collaboration because a shared transformation rule becomes part of the operational contract for how data is prepared. If one team member normalizes output one way and another team member does it differently, downstream logic becomes inconsistent and brittle. A disciplined approach establishes one normalization rule set and uses it consistently, which is exactly what operations maturity looks like. The exam often rewards this thinking because it emphasizes stable, reusable designs. A major beginner pitfall is unintended global changes, where an edit is applied everywhere when it was meant to apply only in specific cases. This often happens when patterns are not constrained, leading to substitutions that fire on lines they should not touch. For example, you might intend to remove a prefix from a log line, but if you remove that prefix globally, you might also remove the same characters from a field value, corrupting data. Safe rewriting limits the scope of the edit to the lines or contexts where the change is appropriate, which can be thought of as a conditional edit. Even without writing conditionals explicitly, the design principle is that transformation should be context-aware. Context awareness can be achieved by matching on stable surrounding tokens, positions, or field labels, rather than by matching on a vague fragment that appears in many places. This is another reason stream rewriting is not purely mechanical, because you must understand the structure of the text and how meaning is encoded. When you design context-aware rewrites, You reduce the risk of hidden corruption, which is one of the most damaging failure modes because it can propagate through pipelines and produce wrong decisions. Another subtle risk is that normalization can hide anomalies if it is used to force inputs into a shape that appears valid even when it is not. For example, if you strip out all non-numeric characters to produce a number, you might convert a malformed value into something that looks numeric but is semantically wrong. In cloud security automation, this is dangerous because it can cause thresholds, counts, or identifiers to be misread without triggering a validation failure. A safer approach is to normalize the harmless variability, like whitespace and consistent separators, while using validation to reject truly malformed data. In other words, normalization should reduce noise, not reduce meaning. When you combine normalization with validation gates, you get the best of both worlds: cleaner inputs and safer decisions. Exam scenarios often imply this by offering an option that cleans up data and continues no matter what, versus an option that normalizes and then validates, stopping when the data does not meet expectations. The safer answer usually reflects the normalize then validate pattern because it prevents automation from proceeding on corrupted signals. Stream rewriting also interacts with iteration and scale because the same transformation may be applied to thousands or millions of lines across a large log set. When you design and edit, you should assume it will be applied many times, which means any mistake is multiplied, and any inefficiency can become costly. Safe design favors simple, constrained transformations that do not invite ambiguous matching and that do not perform unnecessary work. This is not about optimizing prematurely. It is about respecting the operational reality that pipelines handle large volumes and must remain dependable under load. When transformations are simple and constrained, they are also easier to review, which is important because changes to normalization rules can have wide impact. In team environments, transformation rules often become shared infrastructure, meaning many workflows depend on them. So a change should be made cautiously and with an understanding of downstream effects. Even in a beginner-friendly context, it is valuable to build the habit of thinking about downstream dependencies. That habit will also help you on exam questions where a change to parsing or normalization has implications beyond the immediate step. Another helpful way to think about set-style rewriting is as a contract enforcer between stages, much like the role of parameter validation or JSON schema expectations. If Stage 1 produces output with variable formatting, Stage 2 can either become fragile by trying to handle every variation or become stable by expecting a normalized form. Normalization acts as a mediator that makes the contract stable, reducing the complexity required in downstream stages. This is particularly valuable in cloud pipelines where different services may emit similar signals in slightly different ways, and where you want consistent behavior across environments. Contract enforcement also helps auditing because it ensures that downstream logs and outputs follow consistent patterns, making troubleshooting faster and making it easier to spot anomalies. The risk is that if normalization is too aggressive, it can blur distinctions that auditors need. So the safe approach is to normalize only what is necessary for the contract while preserving core identifiers and evidence. This contract mindset connects directly to safe automation design, where each boundary is treated as a point of controlled transformation and validation. When you view stream rewriting through this lens, it becomes a disciplined operational practice rather than a collection of text tricks. Bringing it together, the main idea is that set-style stream rewriting is about controlled, repeatable edits that normalize text without accidentally changing meaning. When you focus on precise goals, small safe transformations, and context-aware substitutions, you reduce the chance of hidden corruption and silent failures. When you normalize whitespace and stable separators, you make downstream parsing and matching more reliable across environments, which is a major risk reducer in cloud operations. When you pair normalization with validation rather than using normalization to force bad data to appear acceptable, you preserve safety and improve troubleshooting clarity. On exam day, the most defensible answers in this area usually reflect the mindset of predictable, minimal change, and conservative behavior when inputs do not meet expectations. In real environments, those same habits keep pipelines stable and keep automation from becoming a source of surprises. If you can treat stream rewriting as a controlled boundary technique, You will be able to build automation workflows that scale, remain understandable, and behave safely even when upstream output is messy. That is the operational value of repeatable edits and safe normalization.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.